So last class, I gave you an overview of Java atomic operations and variables. And you learned a bit about things like compare and swap and atomic long, some of the other low-level mechanisms, the stuff that's available in the Sun, MISC, unsafe class, and so on. And you'll need to understand things along those lines to do the next programming assignment, a portion of it. You'll also need to understand a bit about Java synchronizers. So what I want to do here is give an overview of Java Synchronizer Classes, a big picture view, and then we're going to start talking about one example of synchronizers in Java, which is Java semaphores, which you'll also need for the next assignment. So there's a whole bunch of synchronizers that are defined in the Java class library. We're going to quickly go through all of them right now, just enough so you get a big picture view, and then we're also going to talk about some of the usage considerations, choosing between all the different synchronizers for your programs. So there's a bunch of packages. There's Java util concurrent, and there's Java util concurrent locks, and these define many different synchronizers. You can take a look here for more information about the package summaries. We're going to talk about these synchronizers in this course, and we'll spend a fair amount of time on some of them. You'll get a chance to play around with almost all of them. If we're lucky, we'll get to phaser. We may or may not do phaser, but we'll do everything else here in one way or another. And so I'll show you ultimately show you what these classes do, and you'll get a chance to use them in practice. These synchronizers are used very heavily either in Java applications and/or in Java class libraries. Some of the stuff is used throughout the Java class libraries. For example, condition objects are used by a lot of the bounded queues, the thread-safe bounded queues, things like array blocking queue or linked blocking queue. Those are heavily used there. Other things are used throughout application code, or could be used throughout application code depending on what level of concurrency control you're trying to provide based on the requirements of your apps. One of the simplest forms of synchronizer is something called a Reentrant Lock, which is very similar in capability to the synchronized keyword that's available in the Java built-in monitor objects. We'll talk a lot more about that stuff later. We've briefly touched on it earlier. But a Reentrant Lock supports a mutual exclusion capability that allows one thread to own access to a critical section and requires all the other threads that are trying to enter that critical section to keep at bay or to wait until the thread that owns the critical section is done doing its critical things. And so that's sort of metaphorically like the locking protocol for a restroom and an airplane. And you can see there's actually a bunch of operations here, actually quite a bit more than are available on synchronized with the synchronized keyword in Java, either for synchronized methods or synchronized statements. Reentrant is just a funny name. Sometimes people use the word recursive instead of reentrant. But reentrant basically means that if a thread currently holds the lock and tries to reacquire the lock, that will work properly without deadlocking on itself. And you'll see that there are some locking mechanisms in Java, like StampLocks, for example, that are not reentrant. If you already own the lock, you cannot validly reacquire the lock without bad things happening. But reentrant locks, and we'll see reentrant read-write-locks later, those can be reacquired. Now, if you're taking the class for grad credit, that becomes relevant because for assignment 1B, you'll have to implement a reentrant SpinLock. So understanding reentrancy is important for that. Another property of the Reentrant Lock class is it has to be fully bracketed. And what that means is the thread that acquires the lock must be the one to release it. So again, that's very much like the protocol in a restroom. So, once you're in the restroom, short of you having a heart attack and the cabin crew having to force their way in there with a crowbar to free you, the protocol is that when you're done, you leave, you release the lock. So if you're in there, you lock the door, and when you're done, you unlock the door on your way out. So that's what is meant by fully bracketed. So that's Reentrant Lock. And Reentrant Lock doesn't really differentiate between readers and writers. It just says whoever owns this thing has exclusive access to that critical section, and nobody else can get in there as long as they're obeying the protocol, they won't be able to get in. If they try to get the lock, they'll just have to spin or wait or whatever until they get their chance to get in there. Sometimes it makes sense to differentiate between reading and writing of a resource. And the reason for that is that sometimes you have a lot more readers of something than you do writers. And therefore, you want to allow multiple readers to proceed simultaneously and only require there to be single exclusive access when a writer comes along to change something. So if you have those properties, if there's a lot more readers than there are writers, and the readers dominate, and a couple other things hold, which we'll talk about, then using some kind of read-write-lock may be a win. And so there's something called a Reentrant read-write-lock. A good example of something like this would be the undergraduate catalog here at Vanderbilt on the website. So the undergraduate catalog does, in fact, get updated from time to time, probably once a year. But during the rest of the time, it's just read-only. You're just reading it, right? So you don't actually have to protect it from multiple users accessing it, multiple students or multiple staff or multiple faculty accessing the catalog to read it. So you want all those read operations to proceed at the same time. So that would be an example of something where you read something a lot more than it's written. And then that one time of the year when they update it, you want to have a write lock so that nobody gets sort of a half-baked version of the catalog with some of one thing and some of something else. So I like to think of read-write-locks as kind of this protocol here on steroids, right? So it's kind of beefed up and made a little bit more powerful because it distinguishes between readers and writers. Reentrant read-write-lock as a class has lots of features. So it supports reentrancy, which we already talked about before. It supports this concept called lock downgrading, which means you can go from a write lock to a read lock in a way that is relatively efficient. You can also interrupt the acquisition of the lock, so you can interrupt stuff and it'll return properly with the right exceptions. And it also provides support for condition objects, which we'll talk about later. All these features are both a blessing and a curse. So the good news is there's lots of features. The bad news is Reentrant read-write-lock is really slow. And so as a result, it's probably not a good idea to use it under almost any circumstance. And the reason why it's not a good idea to use it under almost any circumstance is there's now a much better way of being able to get readers-writers behavior, readers-writers semantics in Java, starting with Java 8, via the StampedLock mechanism. And again, we will talk a lot more about this later. StampedLock doesn't have as many features as Reentrant read-write-lock, but the virtue is it's really fast. And so it's typically much, much faster than using a Reentrant read-write-lock. And one of the cool things it supports is the concept of so-called optimistic reads. And an optimistic read is used in situations where you need to protect your data structures from simultaneous access, but most of the time, no one will be writing. So that's, again, kind of like the example we gave with the undergraduate catalog here at Vanderbilt. Most of the time, there's no writers, there's just readers. And so in that particular case, you could optimistically acquire a lock, which basically says you kind of flag the fact that you're interested, or you want to acquire this lock for reading, but there's actually very little or no overhead for that. And then after you're done with whatever you need to do, you then check to see if a writer came along between the time when you optimistically acquired the read lock and now you're done with whatever you needed to get to read the data structures. And if no writer came along, you're done. If a writer came along, however, then you have to kind of throw up the towel or throw in the towel and loop back around again and try again. So it's a very interesting model, and if there's very little contention, very little write access, optimistic reads are super duper lightweight. The other thing that is supported with StampLocks that is not supported with Reentrant read-write-locks is the concept of lock upgrading. So if you have yourself a read lock, you can attempt to atomically upgrade it to a write lock, and if there's no contention, you succeed very quickly. If there is contention, then there's other things you've got to do. And we'll talk about this, and you'll get a chance to play around with StampLock. It's really quite an interesting way of doing things. The next mechanism, which is what you're going to be using in Assignment 1B, along with your SpinLock, is a semaphore. And so a semaphore is another synchronizer that has a count. And there's a couple of different kinds of semaphores. There's binary semaphores, which are either available or not available. And then there's so-called counting semaphores, where you have this count that could be from 0 to n, and it gets incremented and decremented atomically. And we use this in order to be able to limit the number of threads that can get simultaneous access to a group of shared resources, especially for counting semaphores. Binary semaphores are a bit more like a Reentrant Lock with a little bit more generalization built in. So what's an example of a counting semaphore? Well, a good example of a counting semaphore might be something that you would find if you were on the beach in Southern California, where I went to grad school, and very popular, since it's usually 80 degrees and sunny there all year round, are beach volleyball tournaments. And so if you go to almost any beach in certain parts of Southern California, you'll find a whole bunch of beach volleyball nets and a bunch of teams who want to play beach volleyball. Well, there's typically more teams that want to play beach volleyball than there are available courts to play beach volleyball. So how do you coordinate access to that? Well, a very simple way to do it is to have a bag or a basket full of beach volleyballs, one ball for every court. And the protocol is if two teams want to play, they send someone over to the basket or bag of beach volleyballs. And if there's one in the basket, that means there's an available court. So they grab the ball out of the basket or the bag, and they go off and they play. If somebody comes along to play and there's no volleyballs in the bag or the basket, then they have to wait for someone to put it back in the bag. And in theory, at least, once you're done playing, one game or one set or whatever you're playing, whatever the unit of volleyball playing is, then you're obliged to put the ball you were using back in the bag so somebody else can try to get it. So that's an example of sort of a counting semaphore, which keeps track of the number of resources that are available. Now, as you will see, for the Palantir manager that you're doing for assignment 1B and henceforth, you're going to use a semaphore in order to be able to mediate access for many beings, right, Middle Earth beings, who want to access a limited, smaller number of Palantir. So we'll use a counter, a semaphore as a counter, to keep track of what's in use and what's not in use, or what's available. So that's a quick overview. Now, we'll talk shortly about more aspects of semaphores, but it's very important to understand the basic concepts there. One of the things about a semaphore that's a little different from a Reentrant Lock is that the operations need not be fully bracketed. So with a Reentrant Lock and a ReentrantReadWriteLock and a StampLock, for that matter, the thread that acquires the lock must be the thread to release it. So they're fully bracketed. That's what that means. It's a good quiz question, by the way. What does it mean to be fully bracketed? And give some examples. In contrast, you can use a semaphore in a fully bracketed way if you want. And in fact, your Palantir manager protocol and the way it's used by the simulator does in fact use full bracketing. But that's not required. So there's other ways of being able to use semaphores where you don't have full bracketing. And a simple example would be using semaphores to control the transfer of control, or to manage the transfer of control between two threads that are doing some kind of ping-pong-like operation where one of them will do something and send it over to the other, and then the other one does something and sends it back to the first, and then the other one does some stuff and sends it back to the second, and the other one, so basically taking turns going back and forth. And the way to do that is to use a pair of binary semaphores, or one of the many ways to do this is to use a pair of binary semaphores, and they take turns basically incrementing and decrementing each other's semaphores in order to control the order in which things get done. So that's an example where the thread that acquires the semaphore is not the same thread that releases it, because they're going back and forth in a kind of a round-robin-like manner. Yet another example of a synchronizer, which is a very interesting synchronizer, I'll give a quick summary here, and then we'll cover it much more later, is something called a ConditionObject. Unlike the other ones we've talked about, ReentrantLock, ReentrantReadWriteLock, StampedLock, to some extent Semaphore, depending on how it's used. All those other forms, or at least the first three, the ReentrantLock, ReentrantReadWriteLock, and the StampLock, are all used to keep other threads at bay while one thread does its thing. So one thread acquires the lock, that keeps everybody else out of the critical section, it does its thing, then it releases it, and other ones come in. That's how those other ones work. A condition object is quite different. A condition object is kind of the inverse. It says, if I can't make any progress, then I want to go to sleep until someone else changes the state of the program so I could make progress. So it's almost the exact opposite. You keep yourself at bay, you put yourself at bay, you put yourself to sleep until something is the way that you want things. And I'll give you a really cool example later having to do with delivering pizzas and a pizza truck and pizzas and keys. I won't spoil the example now. I'll just give you a quick example from the world of technology, or the way things are built in Java. So if you have some kind of a bounded thread-safe queue, like array blocking queue or linked blocking queue, there are situations where you might want to remove an item from the queue. But if there's no item in the queue, you need to go to sleep until somebody puts something in the queue, in which case they will signal you and you can wake up and try to get the item out of the queue. So that's the kind of thing, and conversely, if you're trying to put something into the queue and the queue is full, you probably need to sleep until somebody takes something out of the queue, and the queue may not be full anymore, right? So these cooperative, coordinating activities that go back and forth between stuff doesn't have to be necessarily in a ping-pong-like relationship, as we talked about with semaphores, but basically putting yourself to sleep or waiting on something until conditions go your way. So that's what a condition object does. They're very, very cool. They're mostly used for infrastructure kinds of things. And they're also used in conjunction with a reentrant lock. So we'll see that condition objects and reentrant locks go together like basically peanut butter and chocolate. There's also a bunch of mechanisms in Java that handle, or synchronizers in Java that handle barrier synchronization. So remember, barrier synchronization is about waiting till a bunch of things are in a certain state before letting them go forward, letting them continue. And there's three different mechanisms that do that. One of the simplest ones is called CountDownLatch, and that's what's used to allow one or more threads to wait on the completion of operations in other threads. And you can use this for a variety of means. You can use it for entry barriers. You can use it for exit barriers. Here's a very simple kind of human-known use of this. If you ever go to a museum, or let's say you go to the Palace of Versailles, or you go to the Forbidden City, or you go someplace that has tourists, you'll often be part of a tour group. And the way that this works is that the tour guide knows that there are 27 people in the tour group, and the protocol is that you don't let people, the tour doesn't start till everybody shows up, right? Because you might buy your tickets online, you might buy your tickets at the ticket window, and for a given tour at the 10 o'clock or whatever, you want to wait till everybody's there, and the tour guide, kind of counts down, says, okay, I've got 27 people expected, I'm counting down, oh, I've only got 26, oh, here comes the 27th person, now the tour can go forward. And you can do similar things, that would be called an entry barrier. You can't start until everything is in place. All the resources are available, all the threads are at a certain point. There's also exit barriers where you can't leave until everybody is done. A good example of that might be somebody who works at a department store or who works at Walmart or Target. You can't close the store until the last customer has left, right? So that would be an exit barrier. So those are examples of things. And countdown latches allow you to kind of count things down, and when the value drops to 0, then anybody who's waiting on something can continue. There's a more interesting and more optimal for certain use cases synchronizer called a cyclic barrier. And this allows a set of threads to all wait for each other to reach a common barrier point. And so it's a bit like a countdown latch. The difference is the countdown latch only can be used one time before it has to be reset. With a cyclic barrier, once everybody reaches a certain point, then they can all start and the barrier automatically resets. So the next wave can come through and everybody will block once again. A good metaphor for this might be some kind of assembly line. Here's an old picture of I think it's the Ford, maybe the Model T Ford assembly line that was popularized back in the, was it 20s and 30s perhaps. And what you have is you have a group of people and a conveyor belt that brings the cars by, and maybe you have multiple groups of people. And the way this works is when the car shows up, then you kind of get everybody to start working on the car, and they all do their own thing, right? Someone's doing the wheels, someone's doing the engine, someone's doing the passenger compartment, or the windows, or the trunk, or whatever. And then when you're done, when everybody's finished, then the car moves down, the next car moves up, and they start all over again, right? So this concept of a cyclic barrier. Things go all over and over again with groups of threads or groups of tasks or groups of agents or whatever you want to call them doing their work. And then the final form of synchronizer dealing with barriers is something that's called a phaser. Anybody who knows anything about Star Trek, not that kind of phaser, right? You don't put them on stun, although that would have been they should have had a stun option for this. This is a barrier synchronizer that's more flexible and reusable and more dynamic than a cyclic barrier or a countdown latch. And the reason why it's more flexible is you can have different numbers of parties or threads or whatever who at any given time will coordinate to do a particular phase. So a cyclic barrier can do phases, but it's always the same number. It's always n, whatever you initialize the thing to begin with. It's n of them. Whereas with a phaser, you can dynamically change the number of things you're going to expect for a given phase. So what's an analogy of something like that? Well, if you've ever watched house construction take place, you typically have work crews that do various things, right? So you have a group of people who frame the house. You have a group of people who put the roof on. You have a group of people who install the plumbing. You have a group of people who install the electricity or the insulation or whatever. So there's always these different phases, but each different phase may have different parties, may have different people, and there may be different numbers of them in each phase. But you still might want to say, you know, the framers have to come in and frame the house. That's phase one. After the house is framed, the roofers come and they put the roof on or whatever. So the idea is you'll have these phases, but there could be different parties, there could be different numbers of parties, threads, or whatever involved in each phase. So it's more dynamic and more flexible, also more complicated. Yeah? Oh, great question. So the question was, you know, if we have phaser, which is this more generalized, more dynamic, more flexible mechanism, what's the reason we have the other ones? Well, one of the answers is historical. CountDownLatch came first, and I think Cyclic Barrier either came out at the same time or shortly thereafter. So they've been there for a long time. Phaser was introduced, so these were, I think, in Java 5. Phaser didn't come in until Java 7. So obviously, if you have old code, you didn't have a choice because phaser didn't exist. Even if you do have a choice, there are some things where Cyclic Barrier or CountDownLatch is just more efficient because they're not as powerful and not as complicated, and the implementation is optimized in ways that phaser isn't because it does more stuff. So it's kind of like, you know, the complexity of making a paper airplane is much less than the complexity of making a 747. And so the cost is higher, it takes longer. Obviously, if you want to fly internationally, you need a 747, not a paper airplane. If you're just trying to amuse your kids, you probably don't need to build a 747, right? You just have to build a paper airplane. So it's about choosing the right feature for the right purpose. But that's a great question. Okay, so those are the key mechanisms. You'll get exposed to pretty much all of them. You get a chance to program with almost all of them. You'll find the pros and cons. So let's talk briefly about them, about the pros and cons. Because as is often the case, as we just talked about, it's very rare that one solution works for everything, either optimally in terms of performance or in terms of complexity, like how hard is it to program. So as a general rule of thumb, you always want to pick the simplest and most efficient version for whatever you're trying to do, because otherwise it's going to be slower and more complicated to use, even though it may be more generalized. So there's this balance between performance and productivity. So some synchronizers or some methods on synchronizers just inherently have more overhead. And sometimes that's necessary. Sometimes you need that. Sometimes you don't. So one of the considerations are locks that spin. So SpinLocks, and in fact, you're about to get practice with SpinLocks in assignment 1B. versus locks that sleep. So some locks spin, some locks sleep. What spin means is they'll sit there and busy wait. They'll keep checking over and over again, sort of neurotically or compulsively, to see whether or not they can get exclusive access to some critical section. Now, the benefit of a spin lock is, in some cases, it's very lightweight, especially if you don't spin very much, because you don't have to put your core to sleep, or your thread to sleep, which is very expensive. However, spinning, mindlessly is also a huge waste of time, right? So there's a trade-off. And for that reason, some of the locking mechanisms in Java actually use this sort of hybrid approach where they try to spin first, or they try to check something in a non-blocking way. If they succeed, they're done, and they've got the resource with a very lightweight way. But in some situations, they can't get it the first time, so then they say, okay, now I'm going to sleep. So you try to spin first, or you try to check something in a non-blocking way first. If that doesn't succeed, then you kind of give up and sleep. So there's a bunch of different hybrid models that are used in Java and other mechanisms as well. Some synchronizers are just harder to program correctly than others. For example, if you use stamped locks are very optimized, but they don't have the reentrancy property that reentrant read-write-locks do. So from one point of view, even though they're more efficient, they're a little harder to use correctly, especially if you have sort of hierarchical callbacks that might require a thread to reacquire the lock more than one time, et cetera, especially if you're using object-oriented frameworks. And I'll show you some examples of this when we get further into the discussions. But essentially, in that case, even though the stamp locks are more efficient, they may be harder to use. So you might end up falling back to a more complex, a less efficient mechanism because it is easier to program. So that's another common consideration. Java synchronizers differ from the built-in monitor objects. So Java has these built-in monitor objects that support the synchronized keyword, synchronized methods, synchronized statements, and then there's also these interesting coordination mechanisms with the notify and notify all and wait methods. And synchronizers are different from the built-in stuff. For one thing, the Java synchronizers, all those classes we just talked about, they're typically written mostly in Java with a few calls to native code, whereas the built-in monitor objects are typically written in C and C++, so they're a little lower level and arguably a bit more efficient, although you have to be careful how you handle that. In both cases, there are low-level methods that are written in native C and C++, so things like compare and swap, int, park, unpark. These are all these very low-level mechanisms. And all the different synchronizers use some of them for the really, really low-level stuff. The synchronizers also typically provide a lot more features and have more powerful semantics, which is often what you expect. The basic low-level stuff is meant to be very efficient. It's basically just a little thin wrapper around some hardware-level features that you'd get. And so they're fast, but they don't do a whole lot. Whereas the synchronizers, the built-in monitor objects, are fast but simple, whereas the synchronizers are reasonably fast but more powerful. But with great power comes overhead, to paraphrase Spider-Man. Okay, so that's an overview of the Java Synchronizer classes. Obviously, we will go into a lot more detail about them as we go through the semester, but this will just give you the big picture view of kind of what to expect in this space. And we will use these synchronizers to implement many different variants of our Palantir manager that we'll be using for the application for all the assignments.